refer to is electrons in a hydrogen-like system. The square modulus is the probability density to locate the electron, right, in the system. Does that make sense? So that square modulus refer to locate the probability for the electron in the system. Now, what do we call that? Give a specific name. We're going to say so this is your probability density from general definition. Now, because that is a probability density to locate the electron in our chemical system, so that we can also say this is your electron density. Do you guys follow me okay? Okay, good. Okay, all right. Now the electron density, when we say electron density, it is really the square modulus of that atomic orbital. All right, now what do you guys think? The probability density. The probability density versus the radius. What do you guys think? What relationship do you have? If I draw the what would it look like? We've been talking about this all the time. It is an exponential. It is an exponential decay, right? Isn't it exponential decay?
Yep.
The maximum value is at I equal to 0. So if I just want to sketch it, it'll be looking like this. Do you guys agree? So it's the probability density decreases as the electrons further away from the nucleus. Alright. Okay, so let's say I'm the nucleus. The rows of those chairs are the atomic orbitals. So we have 1s, 2s, 2p, 3s, blah blah, keep it going. Now, this is not representative because we have a mini electron system. But just imagine all of you guys are gone, just have one of you guys here. Alright, maybe we only have Abby here, only 1 electron. Now, she can have occupation of a different atomic orbitals, but the likelihood to capture So let's say, Abby can go back and forth in many places, but she mostly going to be ended at the row 4. That is 90% of the time she could be. And it's the same idea here. So we're going to introduce a terminology, boundary surface. Okay, boundary surface for the electrons. What is the definition of that? It is a surface within a certain radius away from the nucleus. All right, the spherical surface that can capture within that surface. Alright, so we will have origin. Within a particular radius, you can locate that electron with 90%. That distance, the surface at that particular radius is the boundary surface. Hey guys, that should be okay. Does that make sense? Because the electron can be anywhere. The likelihood decreases by the radius. So what I'm going to say is maybe at this point, beyond inward, that is boundary 90%. At that point, we draw the surface. Now because the s orbital is spherical, so the boundary surface is also is a sphere. Alrighty, so that's about it. So the boundary surface captures a high, proportion 90%, and that's why in many of the textbook you see the s orbital looking like this, a particular radius. This is really referred to the boundary surfaces. Within the range of the radius, we will capture 90% of the electron. The probability is about 90%. And the rest is even further from that surface beyond to the infinity. That will be the rest of the 10%. Okay. All right. Okay. Now, I think that is totally the fun part of the lecture is whatever we learn in the quantum mechanics has all those wave functions. Now we really can apply, right? Okay. All right. The next concept we want to talk about terminology is the radial distribution. The radial distribution function. Okay. Now, to clarify, our wave function through these separation variables the wave function can be separated into the two components, right? One component only depends on the radius r, the other depends on theta and phi. What do we call this guy here? We call this the angular component of the wave function. Now, that's a direct solution for the particle rotation on the sphere, but that is the angular component for the electron in the hydrogen atom. Now, correspondingly, what do we call this part? It is the radial component of the wave function. I just want to draw this up to you that it is not the same as the radial distribution function. Okay, although it has the radial word in it, but those are two different things. All right, so that clarifies. Now let's talk about this. What does it really mean, right? What does it really mean? Okay, so we're going to talk about the radial distribution function. Okay. This is related with the probability to locate a particular particle. All right, so we say all you can do on theta phi, it's up to you, it doesn't really matter. So at this point, with a small volume, how we do the calculation for the probability, guys, or density? We will have a wave function squared times the top. Is that true? Yes, that's the probability to locate a particular point with a small volume of d top. That's our definition. I didn't do anything fancy. Do you guys agree with that one? Alrighty. Now, if it's in three-dimensional space, I want to represent it not by Cartesian coordinates, by spherical coordinates. How do we write the d top, guys?
It's r
How do we
sine
write out
theta.
d top? You have r squared sine theta dr d theta
d
d
phi.
phi. That is a generic. That is a generic, universally correct way to calculate the probability density for a particular system, a particular point with a small volume. It really doesn't matter. You can apply this to any system. That is our definition. Okay, now where we're getting to. All right, now let's take a look at this. Let's take a look at our unique, okay, for the s orbitals. We can approach to the probability density in a different way of slightly different consideration that we can do. All right, it's only for the s orbital. This is your generic calculation. All right, so now how are you going to approach to this? There's a little geometry involved. All right, all right. So I don't have some. Do you guys see this is a? Imagine this is a circle. Okay, how do you calculate the area for the sphere of the circle?
4/3 pi r cubed.
Oh, that has nothing to do with
or the cross.
So like if you
Oh,
have a
area.
sphere, you can have a volume, right? How do you calculate the surface area of a sphere?
4 pi r squared.
How did you guys know that?
We have to use it a lot.
Yeah.
Oh, because of your classes?
Yeah.
Okay, cool. All right. All right. You know, I told you I have a lot of things in my mind. You guys know why? Huh?
Because you're smart.
No. I'm an average Joe. You guys, I'm a totally an average Joe. Okay, so I see one junior person during my undergraduate that comes into classes, every single classes, just sit there, looks like he was daydreaming. You know, sometimes I can be daydreaming, and then I go back to the exam, I got 50. You know, that's me. So I can't do that. I can just go to the classes and not pretend, just like thinking I'm very cool, right? I know that's not me, so I need to study. So that's pretty much it. So I'm average Joe, right? But you guys can think I'm smart, which is, I like that. Yeah. So what I was gonna say is, when I was an undergraduate, of course I like chemistry. The minute I was introduced in middle school, that is the subject that I got attached to. I know right away, at that moment, that's what I like to. Although I also did math and physics as well. Anyway, but when I was in college, boy, no matter if it's a math, physics, or chemistry, we only allowed a pencil, an eraser. The rest, you have to go figure it out. And that forced us, do I like it? Of course not, you know, because I have to memorize everything. Anyway, so type right. Okay, so what you have is 4 pi r squared. Alrighty, now, you guys have to imagine. It's totally not true, but imagine this is a sphere. And then you have another sphere around it. So what do you have? You have a shell. So basically, now let's see if I can draw this really nicely. If it's not, I have a diagram right there. So basically, I can think about I have a sphere, I have another sphere. Can you imagine that one? Okay, now this is your origin. That is the radius to the next sphere, a small next to sphere. The radius can be represented by r plus a small dr differences in that radius. We can imagine that, right? Are you guys following me? Okay?
Mm-hmm.
Yes. Okay. Now, what is the volume? Ooh, I hope you. What is the volume in that little
It's going to be
cylindrical between two spheres that has a thickness? Thickness of dr, right? So you have a sphere, you add another thickness of the dr. What will be the volume in that space? The volume always equal to area times the height or the thickness. Do you guys agree with me? I have a sphere right there. What if I add a little bit of dr? What is the spacing between those two spheres? Is the area times the thickness. Okay. Alright, now here's the diagram. It will be easier. The drawing is more three-dimensional, so you can see the probability of finding the electron, you can for sure do it in this fashion. But for the s orbital, oh no. Seriously?
Yeah.
Okay, I can't believe. Okay, I'll let you guys go. Alrighty. But it's a perfect stop. You guys can review a little geometry and think about how to calculate about the